In Lesson 7-2 here, we're going to be reviewing our properties of powers that we've learned previously, but are important to review before we proceed further through Chapter 7. Our learning targets in Lesson 7-2, not 7-2 and 3, are to be able to evaluate a power, b to the nth power, when b is a number greater than 0 and n is a rational number, to simplify expressions using the properties of exponents, to recognize properties of nth powers, and to solve real-world problems that can be modeled by expressions with nth powers. So here's a review of some of the properties that we've learned about previously, and as usual, the formatting doesn't always come through always real nicely. We know, first of all, that whenever you're multiplying two powers together, and they have the same base, we know that we add the exponents. So when you've got b to the m times b to the n, that is equal to b to the m plus n power. On the other hand, when we have a situation where we have one power, like b to the m, and it's being raised to the nth power, so one base with two exponents, that's a situation where we multiply those exponents. So b to the m and then to the n will equal b to the m times n. Third, when you've got a product of terms within parentheses and then outside the parentheses we have one exponent, that exponent needs to be distributed to everything inside, whether it's a variable or a number. So ab all to the m power is equal to a to the m times b to the m. When dividing two bases that have the same, or two powers that have the same base, we subtract their exponents. So b to the m divided by b to the n will equal b to the m minus n. In this property, if you have a quotient, a division problem in the parentheses, and an exponent outside, that exponent, again, has to be distributed to everything inside those parentheses. So a over b all to the m power is equal to a to the m power divided by b to the m power. And finally, we remember that anything to the 0 power is always equal to 1. So we're going to work through a number of examples that these properties. Here in this first example, we're told that Part A of a multiple choice test contains 25 questions and Part B contains 36 questions. Each of those questions, all 61 of them, have 3 possible choices. How many different ways can a student answer if he or she answers all the questions? So if this student is just purely guessing, how many different ways are there for this student to guess? Well, there are 3 possible answers for the first question, 3 possible answers for the second, for the third, and so on, all the way to the 25th question on the first part of the multiple choice exam. So you're basically multiplying 3 by itself repeatedly 25 times. So that'll be 3 to the 25th power. The same thing is true for Part B. For Part B, there are 3 possible choices, and you're going to have those 3 choices on 36 different questions. So you're going to have 3 to the 36th power. So, in the end, the question asks how many different ways can a student answer if he or she answers all questions? Well, this is a situation where we have 2 powers multiplied together. They have the same base. So this is where we add our exponents. So there will be a total of 3 to the 25 plus 36 power, which is 3 to the 61st power. In example 2, we're asked to simplify this expression. So once again, we notice we have a power times a power. They have the same bases. So this is a situation where, once again, we'll add our exponents. So this is equal to 5 to the 7th power or 5 repeatedly multiplied by itself 7 times, which is equal to, sorry, 2 plus 3 isn't 7, guys. 2 plus 3 is 5. So 5 to the 5th power is equal to 3,125. So once again, that reinforces that property that tells us that when you're multiplying two powers together that have the same base, you need to add their exponents. In example 3, we're asked to simplify this expression, 3x cubed times 2x to the first power. And again, we have a power times a power, so we know to add the exponents in that case. That'll be 3 plus 1, which is 4. And then we also have the coefficients in front, 3 times 2, that need to be multiplied. So we end up with 6x to the 4th power. In example 4, we're asked to simplify 3y to the 4th all squared. And so this is one of those where we have to distribute the exponent to everything inside the parentheses, not just the variables, but their coefficients as well. So the 3 has to be squared, and the y to the 4th has to be squared, and this is a situation where those exponents would need to be multiplied. So 3 squared is 9, and y to the 4th squared is y to the 8th. In example 5, we have a number of properties that need to be applied, so we'll start with the parentheses according to Please Excuse My Dear Aunt Sally. I need to distribute the 3 to everything inside. So the negative 3 has to be cubed, and the x squared has to be cubed. And again, this is a situation where we need to multiply. I'll worry about the denominator here in a moment. So if I simplify what I have on top, the negative 3 cubed will be negative 27. X squared cubed is x to the 6th. Now we need to divide by 3x cubed. So when we divide the coefficients, negative 27 by 3, we get negative 9. When we divide the x's, we know with division, we subtract their exponents. So we'll end up with negative 9x to the 6 minus 3 power, which is negative 9x cubed. In example 6, we have a number of properties that need to be applied again. We need to distribute these exponents. So we'll have m to the 7th over n to the 7th times n to the 5th over m to the 5th. If we multiply top times top, we'll have m to the 7th times n to the 5th over n to the 7th times m to the 5th. Now if we apply our quotient rule, we take these variables that have the same base, and when you're dividing, you subtract their exponents. So I'll have m to the 7 minus 5, which is m squared. Do the same thing with my n's, and I'll get times n to the negative 2. Tomorrow we'll be learning about a negative exponent property, so there's one other possible answer there, but I'll hold off on showing you that until tomorrow. In example 7, we're asked to verify that 3 to the 7th divided by 3 to the 5th is equal to 3 to the 2nd. Well, think of 3 to the 7th as repeated multiplication. It's 3 multiplied by itself 7 times. And 3 to the 5th is also repeated multiplication. It's 3 multiplied by itself 5 times. Well, 3 over 3 is equal to 1, as it is there, and there, and there, and there. So what's left is just 3 times 3, which is 3 to the 2nd. And finally, in example 8, we want to apply these properties to a real situation. So in 1993, the world population was approximately 5.7 billion, which is 5.7 followed by, 5.7 times 10 to the 9th power. The Earth's water supply was 326 times 10 to the 11th cubic miles. What is the person's share of the water? So how much water goes per person? So we're basically looking for water per person. And the word per implies division. So we basically need to take the amount of water and divide by the number of people and apply our rules for exponents. So the amount of water was 326 times 10 to the 11th power. The number of people that have to share that amount of water was 5.7 times 10 to the 9th power. Now rather than just grab a calculator, I can apply my rules for exponents. I'm going to need to take the 326 and divide it by the 5.7, and I will need a calculator for that part, so I'll get 57.193. But with the powers of 10, I know with division, I need to merely subtract their exponents. So each person is entitled to 57.193 times 10 to the 2 power cubic miles of water, which sounds like a lot, which it is. That's the same as, if you move your decimal 2 places to the right, because that's what multiplying by 100 implies, that's the same as each person getting 5,719.3 cubic miles of water. That's a lot of water. One thing to note, though, is that that's the Earth's total water supply, and in actuality, only about 1/3 of 1% of all of the water on the planet Earth is actually usable. So each person would be really given a much smaller amount of water due to the fact that not all of that water on the Earth is usable. Were to be able to apply these properties of exponents, and we've shown multiple examples doing that. To evaluate powers, multiple examples have been shown on how to do that. To recognize these properties and when they are applied, so when to add, when to subtract, when to multiply, and then to apply these properties to real-world problems. If you have any questions, please do not hesitate to email me.